As on most days, Neelu's mother mixed a spoonful of chocolate syrup into a glass of milk and gave it to Neelu, which is her favorite drink. However, on this day, Neelu wanted to have plain milk without the chocolate syrup. Will Neelu be able to separate the chocolate syrup from the milk? Shall we help her? Have you ever wondered about the things in everyday mixtures? Like how lotion feels so smooth, or how whipped cream looks like fluffy clouds? Let's explore more about mixtures and see how they are different from each other. Yes, let's do an activity. For this, we need some materials: a glass tumbler, 200 milliliter of water, and 10 milliliter of milk. Let's pour some milk and water into the glass. Now we have a milky water mixture. So, it's a homogeneous mixture or a heterogeneous mixture? Well, let's consider it. Hey, this situation resembles our previous activity. Could it be classified as a type of heterogeneous solution? Hmm. Yes, indeed. It's a form of heterogeneous solution, a colloid to be precise. A colloid is a heterogeneous mixture where tiny particles are evenly dispersed throughout a medium, however, without dissolving. It consists of a dispersed phase and a continuous phase, displaying distinctive traits like Tyndall scattering. Hello, do we remember our previous activity with the light beam passing through three glasses? Why did the light beams exhibit different behaviors? In the first case, we see the light behaving as it would when passing through pure water, right? In glass A containing salty water, the presence of salt particles dissolved in it does not change its behavior. Refraction and scattering occur due to dissolved salt, influenced by its concentration. This scenario aligns with a true solution. In the second case, when light passed through a mixture of flour and water, scattering resulted in the Tyndall effect, making the beam visible due to small particles dispersing light. In the third case, when light passed through a mixture of milk and water, the Tyndall effect made the beam visible due to fat globules and proteins scattering light, characteristic of colloidal suspensions. What's the size of colloidal particles? The size of colloidal particles typically range from 1 to 1000 nanometers, larger than individual molecules in solutions, but smaller than particles in suspensions. This intermediate size enables colloids to display unique properties, remaining dispersed without settling over time, contributing to their stability and distinct behavior. Some daily examples help show different substances from colloidal solutions with distinct properties. Let's talk about milk. Milk is a colloidal solution where tiny oil droplets are dispersed in water. When we looked at whipped cream, it is formed by dispersing air bubbles in water. And how about jelly? Jelly is made by suspending gelatin particles in water. Have you seen fog? Fog consists of water droplets dispersed in air. And when it comes to paint, it's a colloidal solution where pigment particles are dispersed in a liquid medium. Now, let's talk about blood. Blood is a colloidal solution where various substances such as proteins and cells are dispersed in plasma. These examples highlight how various substances interact to create colloidal solutions, each with unique properties. Now, let's delve into some fascinating history. Throughout history, perceptions of pure and impure substances have evolved. Ancient alchemists aimed to transmute base metals into gold.
prioritizing purity. Antoine Lavoisier's work in the late 18th century laid the groundwork for modern chemistry by introducing the concept of chemical elements. John Dalton's atomic theory in the early 19th century further classified the distinction between pure elements and compounds. Advancements in analytical techniques in the 19th and 20th centuries enabled precise identification and characterization of substances, enriching our understanding of purity and impurity in chemistry.